This is 8th grade activity 4.4. It's actually going to also include our lesson. The activity students will compare tables and graphs of linear and nonlinear function. The standard covered is 8EE5, 8F3, and 5. The page numbers out of the hardcover book are 168 through 173, and out of the practice journal, pages 89 through 92. Today we're going to be working with linear versus nonlinear functions. Remember, a function is when we can set up and something happens to our x to create our y. So today what we're going to do is we're going to look at a couple of examples. Here we've got some rectangles, and we're going to complete the table to show the sequence that's happening between these similar rectangles. So there's two things that we can solve when we work with rectangles. One of them, we can find the perimeter of the rectangle, and the other is we could go through and we could actually find the area of the rectangle. So those are the two things that we're going to work with today, and we're going to actually graph those. So first of all, our table is giving us numbers that they want us to use for x. So in the first situation, this little green rectangle that they want us to put a 1 where x is. So this is now going to become 1, and this is 2 times 1 here. So 2 times 1 would now give us 2 there. So we're going to go ahead and find our perimeter because we've got p, x, and p. So our y is the same as our p here. So if we want the perimeter of this rectangle, well, we've got 2 plus 2, and then another 2 between those would give us 6 for our perimeter, okay? Just for future reference, because we will be using it shortly, let's also go ahead and find our area of that, and I'm just going to go ahead and write that in a different color. So the area of that rectangle, well, we find area by doing base times height. So 2 times 1, or length times width, would give us 2 for our area. Okay. All right, so now we're going to look at the next rectangle. So the next rectangle is similar, which means it still follows that pattern of this is going to be x and this is going to be 2x. Okay, so we still do that. It's just that they're telling us that x this time is going to be 2. Okay, so wherever we have x, we're going to put a 2. So this becomes 2. And then here, this would be 2 times 2, which is going to give us 4 for that side. Okay, so our perimeter, well, we would have 4 plus 4, which would give us 8, 9, 10, 11, 12. So we got 12 for our perimeter there. And while we're at it, we'll go ahead and find our area. So there we would do 4 times 2 would give us 8 for our area. So we'll go ahead and circle that because we'll need it for later. Okay, so our next one, still following the same rule of x for the height and 2x for our width or our unit going across. So we're going to substitute in a 3. So this x becomes a 3. And our 2x would be 2 times 3, which would give us 6. Okay, so to do our perimeter, well, we would do 6 plus 6 is going to give us 12. And then 15 plus that would give us 18 for our perimeter. Our area, on the other hand, would be 6 times 3, which would also give us 18. So in this one, we had the same area. Okay, the next one, they're going to have a substitute in 4 where x is. So our height would be 4, and our width across here would be 2 times 4, or 2x. 2 times 4 would give us 8. So for our perimeter, well, 8 plus 8 would give us 16, plus 4 would be 20, plus another 4 would be 24. And our area, well, that would be 8 times 4, which would give us 32. Okay, and our last one, we've got 5 for our x. So this becomes 5, and this becomes 2 times 5, which is 10. So 10 plus 10 is 20, plus 5 is 25, plus another 5 would give us 30 for our perimeter. And our area, well, 10 times 5 would give us 50. So we're going to go ahead and do 50 for our area. Okay, so there we've gone through and done the hard work. So just understanding how to pull that information. So now what they would like us to do is they would like us to go through and actually graph each of these scenarios. So right now I've got my perimeter one out here. I'm going to go ahead and graph that and see what it looks like. So my X was 1. My P here, which was my perimeter, was 6. So over to 1, up to 6, approximately somewhere in there. It's not going to be perfect on my smart board. Sometimes it's slightly off. Okay, so my next one was, well, when X was 2, the P or the perimeter was 12. And when X was 3, my perimeter was 18. When X was 4, my perimeter was 24. And when X was 5, my perimeter was 30. So it looks like a pretty straight line. So they ask us, decide whether each pattern is linear or nonlinear. So we haven't discussed linear versus nonlinear, but if you look at the word linear, has the word line in it. Now we have to understand that line actually means a straight line, perfectly straight line. So in this case, if I were to connect my dots, although I'm slightly off on one of them, it looks to me like we have a pretty straight line going on through here. So this is what you would call a linear pattern. And we'll learn in this lesson actually how to determine, without having to graph it, how to determine whether we have a linear function or not. So here we get to see the visual of what a linear function looks like. So let's go ahead and do the same concept with our area. So I'm going to move this down slightly so that we can actually see both graphs at the same time. Okay, so here's our area graph. And we have all of our areas circled up on our rectangles there. So let me shift this over. Okay, so I'm going to go ahead and graph my information. Well, I need to fill in my table. So my area, when it was a 1, for my X, my area was 2. And when my X was 2, my area was 8. When X was 3, my area was 18. And then 4 and 32, and 5 and 50. Okay, so we're going to go ahead and now graph this information. So I'm going to go over to 1, up to 2. Oops. Okay, and then over to 2 up to 8. Over to 3 up to 18. Over to 4 up to 32. Over to 5 up to 50. So 50 is clear up here. Okay, so now when we look at this one, it looks close to being a straight line, but if we actually were to connect those, you can see that it actually is curving upward. Okay, and yours will probably look a little bit better than mine because my smart board is slightly off as I'm graphing these. But this would be where we ended up with what you would call nonlinear. It's not a perfectly straight line. We see quite a bit of a curve down in this part, and I'm sure that you could see it a little bit better on yours. But we do have a curve going on between these points, so this would be nonlinear. Okay, so that's working here where we've done this 2 different things with some units off of a rectangle and found out that when we find the perimeter, that is considered a linear function. And when we do the area, it's nonlinear. Okay, we ended up with a curve. So we're going to go ahead and do a couple more of these where we're going to graph our data and look at our data points. Okay, so here it says, graph the data in the table. The nice thing is that graph's already set up for us. Decide whether the graph is linear or nonlinear, and then compare the 2 falling objects. Which one has an increasing speed? So the first one, we have a falling parachute jumper. So at T on this is representing our time. I know I have that kind of cut off on the bottom, and I'm not sure if it tells you that in your book or not. It does. I accidentally cut off the very bottom of these graphs, but this T down here actually is representing time. Okay, so when our jumper jumps out at 0 seconds, their height is 300 feet above the ground. So over to 0 up to 300, we're going to go ahead and mark these off. It looks like every box is representing 30 on this parachute jumper. So this would be 270 here. So then 300 would be right here. Okay, our next one is over to 1 up to 285. So over to 1 up to 285. So this one's 240 right here. And then that would be 270. So 285 is going to fall kind of in the middle of that box. I know mine's slightly off. The next one is over to 2 up to 270. Okay, 270 is right on a line. Over to 3 up to 255. Over to 3 up to 255 is going to be in the middle of our next box above 240. And then over to 4 up to 240. Okay, so those are the only pieces of information that we have. Obviously, they haven't hit the ground yet, but it looks to me like we're going every time we go over a box, we go down half of a box. So this would be what you would call linear. I know my dots are slightly off, but it looks like a pretty straight line. Okay, so our falling bowling ball. So same concept, our graph is set up the same way. We have the time on the bottom once again. Okay, and every box that's going up for the height is worth 30. So like this would be our 270. Okay, this would be 210 here and so forth. Okay, so we're gonna go ahead and at second 0, it's 300 feet above the ground. So they start off the same, at the same point. At 1 second out, it's at 284. So we're gonna have to kind of guesstimate. That's almost in the middle of the box, slightly less than half, but we're not really gonna see that when every box is worth 30, okay? So we're gonna go ahead and go over to 1 and about halfway up this last box. Not a whole lot of difference between second 1 here and second 1 on the bowling ball, okay? The height was 1 foot difference. Okay, so the next one we're gonna go at 2 seconds, it was at 236. So over to 2, up to 236, you can see that's gonna be just under our 240. Okay, at second 3, over to 3, it was at 156. So 150 is gonna be this line here. So 156 is a little above that. And then at second 4, over to 4, up to 44. So this is our 30 block, right? So 44 would kind of be in the middle of that block and the 60 block. So somewhere in here, whoops, my board's off on the bottom. Somewhere in there. Okay, but we can notice just from doing this, if I connect my dots, that it fell off dramatically as we graphed those. Okay, it's not a gradual fall, it's happening very fast. So this would be a nonlinear, because that's not a perfectly straight line. Okay, and it also wanted us to compare the two falling objects, which one has an increasing speed. So if we notice, our parachuter looks like they're going at the same speed. They're dropping about 15 feet every second. If we were to go through and kind of compare our height change to our second changes. Okay, in our next scenario with the bowling ball, well, it starts out 16 feet in the first second, but then it drops pretty dramatically, and by second 2, it had dropped from second 1 another 48 feet. So there was a change from 16 feet to now 48 feet to about 100, not 100 feet, but 80 feet drop. So this one is dropping much faster. So our bowling ball says which one has an increasing speed? That would be the bowling ball. Okay, so basically out of this activity, you were just working with understanding linear versus nonlinear. They gave a couple of real world scenarios so that you could understand the difference between these. They gave you the data that you needed, and then you were able to visually see the graph. So once again, a linear graph is going to show us a perfectly straight line, whereas nonlinear is no longer a perfectly straight line.